So let's have a look at the geometric Brownian motion then. So you remember from last week's talks that if we look at uncertain price processes, we typically have described this process in terms of an ETO process, which consists typically of a growth term and an uncertainty term. So in particular, this geometric Brownian motion process here describes the P, price or profits or whatever it might mean. So the uncertain parameter, the uncertain variable here, is price dp. So the change in price is measured as a growth part, which is proportional to price or p itself, with a growth rate mu, and multiplied by dt. So that's the drift rate or growth rate. Mu is the drift rate actually, and sigma here is measures how large uncertainty is. So it's called the volatility. So this second term is the volatility parameter, the uncertain part component of this price process. And again, it's proportional to p for the geometric Brownian motion, and this dz or dz if you wish that you see there actually is called the Wiener increment. So basically is a small time increment which is itself distributed in a Gaussian or in a normal way, so and grows larger and larger with time. So that's a geometric Brownian motion. So again, this mu is the rate of growth. So it means that if we would only have this growth rate part, we would have this equation over here, dp equals mu times p times dt, and you can easily figure out for yourself that means that p itself is indeed growing like this growing perpetuity form that we just had a look at in the previous slides. And sigma is the uncertain part here, so it's the volatility. So you'll see the other stuff that I said, and as long as it's mu and the sigma and the are constant, this is what's called geometric Brownian motion. So let's have a look indeed at a price process which follows this geometric Brownian motion with this drift mu and with this volatility sigma. Well, in that case, actually, we will be interested in what's the expected value of this p at the time t, so sometime in the future. So this expected value turns out to be dependent on what its value is today, of course. So it depends on p at time 0, but again it grows at a growth rate mu, so e to the power mu t times p. So this is not completely obvious in a way. So essentially what you might want to do is have a look at Hull's chapter 14, where he derives this. So one way of seeing this is the following. So let me take a look at this on paper. So if we have uncertainty, we have p now following this geometric Brownian motion with the drift term times the plus the uncertainty term. So one way of seeing what the expected value of p in the future is by rewriting this and by seeing that actually if we take instead of p the e to the power mu t times this price, what's that? Well, there's the derivative, an increment of this thing. Well, how do we compute that? Well, using product rule essentially. So this gives rise to two parts. So it gives rise to the derivative of the first part minus mu times e to the power mu t p dt plus derivative of the second part to the minus mu t times dt, and that of course is minus mu t plus e to the power minus mu t. Now let's plug in what we know, that dp over here, we know what it is. Let's plug that in. Mu times p dt plus sigma p dz, And now you see that these first two parts actually are the same, but with opposite signs. Here's a minus, here's a plus, so these two cancel. This one cancels against that one, and the only thing that remains is this part over here, e to the power minus mu t sigma p dz. So what you see is that the increment over time of this expression, so not p itself, but if you wish p discounted with its drift rate, is something which has no drift. It only has stochastic terms. So it might go up or down, but there's no direction to this movement. So that means actually that if you only have this uncertainty part which goes up and down in like manners, that means that the expectation of some e to the power mu tp in the future must be equal to its current value. So at t equals 0, minus p time t will be p at time 0, or in other words, p0. So now what's this? That's actually e to the power minus mu t times the expected value of p of t, so that equals p0, or in other words, the expected value of p itself in the future is just e to the power mu t times p0, and that was actually what it said on the slide. So if you look at in whole, I think you find a different explanation of why this is true. So that explanation actually involves recognizing that if p follows this geometrical Brownian motion process, then actually the log of p, or the natural log rather of p, follows almost the same process, but there was this particular Ito term, which, well, you'll learn about if you follow the derivatives course in particular. What this means essentially is saying that this log of p, it follows not geometric Brownian motion, but Brownian motion itself. So there's no p or log of p on this right hand side anymore. And what this tells us, or what the interpretation of this is, well, this log of p in the future is actually normally distributed. Normal with, so the log of p at some time t in the future will be distributed according to the normal distribution with a mean mu minus half sigma squared t plus log, ln of p at 0, and the variance, or a standard deviation rather, sigma squared of t. So if we know that this log of p in the future is going to be distributed normally, so according to the normal distribution, we can actually compute the value of its expectation, or rather of the expectation of e to the power log p, which is p itself. So that allows us basically to do this computation. That's what Hall does in this chapter. So that's a sort of a bit more cumbersome computation, but if you really want to figure out, do have a look at that. Okay, so that was an intermezzo, just to make sure that we have some idea where this e to the mu t times p as the expectation of p comes from. But for us now, it's actually sufficient just to know that the expectation of GBM process p with a drift rate mu is just e to the power mu t times p. So that's what we want to know. So because in that case we can actually also compute the value of a growing uncertain perpetuity. So what is that? The expectation of the value, or the value essentially is the expectation of future cash flows. It's e of p in the future, which we now know what it is. We have to discount it by e to the minus t minus rt. So this is the expected cash flow, the flows of profits, profit flow I should say. We have to add them up, or in continuous time I have to take the integral. So now we know what e of p is. It's again this e to the power mu t times p at the current time. Well, what we find here is actually again the same integral which we could do as we just did before, leading to p to the power r minus u. So even if we introduce uncertainty, the value of this growing perpetuity with uncertainty is actually the same as the value without uncertainty. Okay, so that was geometric Brownian motion. A quick reminder, for those of you who have seen this already. So let's now go on in the next video to looking at the Bellman equation, because that's basically what we're after. We're going to look at this Bellman equation, which will allow us to compute the option value, but we'll have a look at this in continuous time rather than in discrete time. So let's see you in the next video discussing the Bellman equation.